Hi everyone, thank you very much for your introduction. In this presentation, I will show a novel framework for enabling approximate computing on heterogeneous architecture. The name of this framework is SYprox and is very similar the name to the previous work that has been presented by Professor Cosenza, because we decided to give more or less the same name to our framework. So starting with C, that means that the framework has been implemented using the SYCL programming model, and then prox is for approximate computing. So we are enabling approximate computing on heterogeneous architecture using the SYCL programming model. Okay, before starting this presentation, I will give a small introduction on what is approximate computing and what are the most important software techniques in approximate computing. And then I will show the main contribution of this work. And in particular, I'll explain in detail the SYprox framework that is composed by an API that define how we can build approximate computing program in SYCL using the SYprox library. And then I will focus on a novel approach to data perforation. So a novel approach for approximate computing data perforation that is called host perforation that has been implemented in this library. And then I'll show how we can combine different kind of approximate computing techniques in a single program using the SYprox library. And in conclusion, I will show some results on different kind of architecture, in particular on GPUs from different vendors, from Intel, NVIDIA, and AMD, for demonstrating the portability of our library. Okay, so let's start with this introduction. The idea behind approximate computing is that there are some applications where it's possible that we have a small error in the final output of the application, and we can exploit this error for improving the performance. And this happens, for example, in domain like machine learning, neural network, image processing, and also in general in computer vision. And when we talk about approximate computing, we always have to think to a multi-objective problem where we want to optimize the performance, but at the same time, we want to have a very small error. Because when we apply an approximate computing technique, we are also introducing an error inside the application. So we want to minimize the error and maximize the speed up of our approximation. And sometimes we can also consider a third objective, that is the energy consumption. So we want also to optimize the energy consumption using approximate computing. But in this presentation, we will focus mostly on the performance side, and we will see how we can improve performance with approximate computing. Let's start with the first technique, software technique for approximate computing, that is data perforation. The idea is that most of the time, the data contains some redundancy. For example, let's think to an image where we have near pixel that have a similar value. And what we can do is to apply perforation. So we skip the loading of some element inside the memory so that the computation is performed on a perforated image, and we do the computation only on some of the pixel in the image. For example, in this picture, at the center, we apply the perforation on the row. So we are skipping some of the row of the input data. And then after the computation, we can apply some reconstruction technique. For example, we can apply linear interpolation between the near pixel, and we can reconstruct the missing data. So here we have two approximate computing techniques. The first one is data perforation, and the other one is reconstruction, that is used for reducing the error introduced by the approximation. And another common technique that is very used on the software side is mixed precision. So usually in an application, we can have different requirements in terms of precision. For example, for parts of the application, we need 64 floating point, but for another part of the application, we may need a small precision format. For example, a null floating point precision. And when we use lower precision format, we have some advantages. For example, we have faster computation because we can exploit specific hardware for lower precision format, and also we are using less memory footprint. And if you think to an execution model like the one, an host device execution model, if we use lower precision format, we can transmit more number, for example, from a CPU to a GPU. And on the other hand, when we use lower precision format, we are limiting the number or the range of value that we can represent. So this means that we will introduce an error in the final output. So we have to understand for which part of the application we want to use an higher precision format and for which part we want to use a lower precision format. And um, in our work, we decided to address three main challenges. The first one is that there is no portable interface that implements approximate computing technique on heterogeneous architecture. So all the framework that has been implemented, they usually target a specific architecture and they apply the approximation for this specific architecture. And the other point is that most of the data perforation technique do not exploit the host device execution model, where you have usually an host and then you have an accelerator where you do you offload the computation. And the last point is that all the framework do not allow to mix together different kind of approximate computing techniques. So we decided to develop this framework that is called SYprox. And the first contribution of SYCL is a new portable interface for approximate computing that is based on SYCL. So we extended the SYCL semantic for implementing approximate computing feature in SYCL. So we are portable by design, performance portable by design. And we implemented a novel approach that is called the host perforation that fully exploit the host device execution model. And we will see later in detail this host perforation. And also with SYprox, we can combine together mixed precision with data perforation, and we can improve the performance of our application by combining all these techniques together. So let's start with an overview of SYprox. Here you can see a snippet of code where that has been implemented using SYprox. The code is very similar to a SYCL code, where you have buffer and accessor, you have a submit command for executing your computation on a device. And here, the important thing is that I want to explain how it works, the SYprox API, when you try to apply all the approximate computing techniques. You start with some data that are on the host, for example, in floating point precision. And then you can apply host perforation that is implemented through the perforated buffer that extend the buffer of SYCL. And the host perforation simply skips some element in the input data. For example, here we skip some of the row of the input. And then we can also specify the target precision format that we can use for this data. And after this, we send the data to the device that can be, for example, a GPU. And then here, during the computation, we can apply online the device perforation that has been implemented through the perforated accessor that extended the accessor of SYCL. And then we have the kernel computation. And finally, we can apply our reconstruction technique so that we can reconstruct the missing element, and then the data come back to the host. So what we can see here is that with one single code, using our SYprox library, you can mix all the technique like host perforation, mixed precision, and device perforation and reconstruction. But let's go a little bit into detail. Here we can see an accurate SYCL code. You have the SYCL queue that define where you want to submit your computation, on which device you want to submit the computation. In this case, we specified the GPU selector, and then you have buffer accessor that define how the data are accessed on the device. And then you have the parallel for where the computation happen on that specify the computation that happen on the device. So the SYprox library just needs some small changes into the SYCL application to apply approximate computing. For example, if we look at device perforation, we have just to modify the accessor with a perforated accessor. And the idea of device perforation is that we send the data from the host to the device, and then the perforation happen on the device. So the perforation is applied on demand during the computation. And after the computation, the data are sent back to the host. Let's go a little bit into detail of the perforated accessor. As I said, it extends the accessor of SYCL, and in particular, we have another parameter inside the template parameter of the accessor that is the perforation schema. The perforation schema defines how the data are perforated during the computation. For example, here we defined a row schema where we skip some of the row of the input data, but we can define any kind of perforation schema. So the user can customize the perforation schema and just specify this perforation schema inside the template parameter of the perforated accessor. And there is another parameter that is the skip factor that defines the degree of approximation. So higher is the skip factor and higher is the number of rows that we are skipping. The second approach to perforation is the host perforation. This is the novel approach where we perforate the data before sending this data to the device. So we start with some input, then we perforate on the host, and then we send the data from the host to the device. In this way, we are reducing the number of data transfer that we have, and most of the time, we increase a lot the performance of our application because most of the time is spent in the data transfer instead of computation on the GPU. And for this approach, we implemented host perforation using the buffer of SYCL. So we extended the SYCL buffer with a perforated buffer. And as for the accessor, we have always a perforation schema that define which data we want to skip. And also here we used a row schema, but we also implemented a column schema and also some perforation schema for one-dimensional data. And you can implement your own perforation schema also using more than 3 dimensions. And usually the idea is that we want to support all the dimensions that are supported by the SYCL programming model. And always the skip factor that allows to control the degree of approximation. So the other technique that we implemented in SYprox is the mixed precision. So you can specify into the P buffer the type of data that you want to use for your data. For example, you can specify for the input buffer the half floating point, and for out buff the floating point. And then the kernel is performed using mixed precision between half floating point and floating point format. What we are not supporting here is inter-buffer mixed precision. So inside the buffer, the data are all float or all half precision, but we will try to support this in the future. And the type of data that we are supporting are the ones that are supported by the SYCL standards. So floating point, half, and brain floating point. Another very important thing of SYprox is that we can combine approximation. But why this is important? First of all, if we look to individual techniques like mixed precision, we can notice that we have a lower error, like 1% of error for this application that is an image processing application, and we can achieve up to 1.8 times speed up. And if we look at device and host perforation without considering the reconstruction, we have up to 1.2 times speed up or 1.3 and an error up to 50%. This is because we are not applying a reconstruction technique. And if we apply a reconstruction with perforation here, we can see that we have a lower error because it's only 1.5% of error, and we have a speed up to 1.5 times. And the important thing is that we can mix all these techniques in order to expand the approximation space, so we can have more configuration because we can use mixed precision together with the reconstruction and perforation, and we can improve the Pareto frontier. So here you can see that in the last plot that shows all the approximation combined with mixed precision, perforation, and reconstruction. We achieve up to 3 times speed up and an error that is lower than 6%. So we have a huge improvement in performance with a very small error. When we talk about approximation, we have to first of all do an error analysis. So we decided to select some benchmark, and we executed this benchmark for a different input. And here you can see on the y-axis the mean absolute percentage error, and what is shown here is a box plot, so that we can see what happens when we have different kind of input and application. The takeaway here are that the error introduced by the approximation depends on the application. So for example, Sobel tree has a completely different behavior compared to the blur filter, but also that the error introduced by approximation depends from the input data. So for example, for the same application, for Sobel, we have an error that go from 5% up to 30%. And this depends on the type of image that we are using as input. And the other point is that the type of approximation schema that we are using, so if we decide to perforate the row or the column, or depending on the type of perforation schema that we use, we can have a different error also for the same application. So it's very important to define for each specific application a different perforation pattern. And the other point is that the type of reconstruction that you are using also impact the error. And here we have 2 types of reconstruction. The first is input reconstruction, where the data are reconstructed in a fast local memory, shared memory for the CUDA memory model. And then the computation is applied on the same number of elements of the accurate application. And the other way is output reconstruction, where the computation is done only on part of the element, and then the missing element are recomputed after the computation. And these 2 kinds of reconstruction technique can generate a different error in the final application. Performance side, we can notice that the host perforation outperformed the device perforation, and we divided the plot in 2. So we have the data transfer speed up and the kernel speed up. So in the first plot, the host perforation always achieves a speed up of 2 times. This is because we are halving the number of elements that on which we are doing the computation. So the number of elements that are transferred to the device are divided by 2. And for the device perforation, we do not have any speed up because all the data are sent from the host to the device. Differently, when we look at the kernel speed up, we can still notice that the host perforation outperformed the device one. And this is because when we apply host perforation, the data in memory are aligned, so we can have better memory access on the GPU. So the number of cache hit that we do in the host perforation is higher compared to the one of device perforation, where we have a lot of cache miss. So we have higher improvement also for the kernel speed up in host perforation. In this slide, we show a comparison against a state-of-the-art framework for approximate computing, that is HPAC. this framework implements perforation in OpenMP. And the green Pareto frontier shows the HPAC Pareto frontier, while the red one is the SYprox Pareto frontier. And how we can see the SYprox Pareto frontier in all the picture outperform the HPAC Pareto frontier. This is mostly because host perforation is more performant than device perforation that has been implemented in HPAC, and also because HPAC do not have any reconstruction technique. So the error is higher for the HPAC framework. And the other very interesting things to notice is that in HPAC framework, because you have to use Pragma OpenMP, sometimes the transformation that are applied to the code generate illegal instruction or generate infinite loop. So when you use SYprox, you have a higher control over the application. So you can apply this technique automatically, but you can still change your code in order to avoid any kind of issue related to segmentation fault or infinite loop. In this slide, we show some results on different kind of architecture. So here we have the results of SYprox on AMD, on Intel, and NVIDIA GPUs. And this is just for demonstrating that using SYprox, we can port our approximate computing techniques on all the hardware that are supported by SYCL. And if we want to support other hardware, we can just implement a new backend, and we have for free also the SYprox library. In conclusion, we showed a novel framework for enabling approximate computing on heterogeneous architecture, and we implemented a novel approach to fully exploit the host device execution model that is host perforation. And we show how we can combine different kind of approximate computing techniques on heterogeneous architecture, and we show an experimental evaluation on heterogeneous GPU from different vendors. So this work has been presented to ICS this year in 2025, and that's all. Thank you very much for this presentation, and I'm open to any kind of question.